Hello. Now we go to the session on logistic map. This actually a map is a function which is depending upon its own variable. See, actually this function was originally developed to study the population growth of some species, for example rabbit maybe in take. So suppose P is the strength of a population of rabbits in particular year. And the next year when come the population becomes 2 times. That is the population is doubling. Then for the second year, third year the population will be 4 times that. So see, this is the equation showing that this is the population next year, this is the population this year. So it is doubling. So generally we can use instead of doubling, suppose this is depending upon some factor R. So we can take generally R is the growth rate we take. Here 2 is the growth rate because it is doubling. So generally if you take R as the growth rate, then the population next year will be equal to R into Pn. So actually when this is going on like this, the population will be doubling each year. So there won't be no space on earth for humans to be live, because the entire earth may be filled with rabbits if this is continuing. So nature will take some preventive methods to control the rapid rate of the population of any species. For example, in the case of human also, there may be some natural control by means of natural calamities, just like a flood, earthquake, or nowadays is a corona, the COVID disease like that. It is a tendency of the nature to control the incessant growth of this population. So then suppose A is a controlling factor, something like that. The growth controlling for some is called the attenuation factor. Then the equation can be modified as R into Pn into 1 minus Pn by n. This is the population at this time, and Pn plus 1 is population at the next time. Then the A is called the attenuation rate. Watch this equation once more. Suppose the population at this year is equal to the attenuation rate, then for the next year it will be P into N into 1 minus A by A, which is equal to 0. That means when the population is equal to the attenuation rate, next year the population will be 0. So this is the maximum value of the population attenuation rate. So there will be some controlling factor to avoid this. We divide this equation by the attenuation factor A. You get as Pn plus 1 by A. Here also right side Pn by A into 1 minus Pn by A. Now we substitute this Pn plus 1 by A. It is a ratio. This is a ratio of the next year's population to the attenuation rate, and Pn by A is this year's population to the attenuation rate. We take this as xn. So this will be Pxn plus 1. So there is just a ratio, and R into the control factor xn into 1 minus, here also xn. So this is the logistic map equation, because this is xn plus 1 is the ratio of the existing population of next year to the attenuation factor, and xn is the ratio of the population of this year to the attenuation factor. So the value of x is less than 1, because when x is equal to A, you have seen the population growth will be 0, and the control factor R is between greater than 1A. You can see the effect of R when the value of it increases 1 to other values. There will be very dangerous values when R is reaching certain value greater than 3, like that. So generally this can be expressed as a function x and plus 1 we write it fx, some function is equal to r into xn into 1 minus xn. So this is r into xn into 1 minus xn. That is, the function depends upon its own value in the future. This is called a logistic equation. This is the logistic map equation. Now you can see some properties of this logistic function. See, the root of logistic equation x is equal to 0 and x is equal to minus 1. See, this is the equation. Xn plus 1 is r. When you solve this equation, you get when x is equal to 1, this value is equal to 0. And when x is equal to minus 1, x is equal to 1, this equation is equal to this equation. So the root of this equation is 1. And 0 is there, how x is equal to 0, equation is equal to 0. Now we differentiate this equation. See, when you differentiate this, you get df by dx is equal to, you take this xn to the right side, so r into 1 minus 2xn. See, when you take xn to the inside this bracket, this will become r into xn minus xn square. So dfx by dx will be equal to r into differentiate of xn is equal to 1 and xn square is equal to minus 2xn. So difference df by dx is equal to r into 1 minus 2xn. See, this equation when x is equal to 1, this equation is 0. So one is one root. Then when xn is equal to 0, then also left side is equal to right side is equal to 0. Equation is 0. So these two roots are xn is equal to 0 and xn is equal to 1. And the differential is r into 1 minus 2xn. Or minus 2xn. See, when the differential coefficient is equal to 0, that is 1 minus 2x is equal to 0, we have x is equal to 1 by 2. So this function has a maximum or minimum at x is equal to 1 by 2 because dy by x is equal to 0. When you take the second differential, we get d square f by dx square is equal to minus r. Therefore, this is a minimum because the first differential is 0 at x is equal to 1 by 2 and second differential is negative. So definitely 1 by 2 is the point where this function has a minimum value. That means after some repetition, this may be repeated sometime, the rate of change will be taking this according to time, then it will be converging to some fixed point because it is going to a minimum value. That is why it is converging. It is converging to some fixed value. And this fixed value is usually called as the attractor. So after attractor, the repetition will be the same value. Here, the values of interest of the r, but depending upon the value of r. So usually the value is taken between 0 and r, 0 and 4. You can see various types of effects of this logistic map when the value of r is changing from 0 to 4. I have taken a long table in my notes which shows the value of the function at different values of r. Now we can prepare a Python program may depending upon this equation, the logistic equation, and plot the graph. The graph I have already sent to you. See, this is the equation we are using. So this is one of the graphs. See, you can see that the initial we have already almost avoided because this is same. So you can take any initial value for x and maybe 0.1 or 0.24 like. After some repetitions, you get the same value. So this is almost the same value of the function. And after, see, when you gradually increase the value of r, So this is depending upon the change of value of R. At one particular value, you can see that the plot is splitting into two. That means at these 2 points, the population will be oscillating between a high value and a low value. So there is some kind of confusion. See, 1 year may be too high, second year may be too low. Then this thing is repeated for a long time. If we are still changing the value of R, then reaching this point, so this point where the graph is dividing to a maximum and minimum is called a bifurcation. The graph is splitting into two, a bifurcation. A further increasing of R, you can see that here again there is a splitting, a bifurcation, and here is also a bifurcation. Now the ratio of the population will be oscillating between 4 values. Then here you can see, if you magnify the graph, here there are 4 values, here also there are 4 values. Now it is oscillating between 8 values. If you go further, it will be oscillating between 16 values. If you continue the value of like that, there will be utter confusion. It is uncontrollable. And this region we call the chaos, where there won't be any order. It will be multiplying at uncontrollable rate. So here it is 2, so bifurcation. Here again bifurcation into 2. It is also bifurcation into 2. So total will be 4 cycles, and this will be here also 4, here also 4. So 8 cycles. The next time will be 16 cycles. That will be leading to chaos. Now the value of y using Monte Carlo method. In Monte Carlo method,